Hello everyone, I present you DCN squared, interplay of implicit collision weights and explicit cross layers for large-scale recommendation. First of all, the agenda. We'll discuss motivation, architecture, offline and online evaluation, as well as scaling and productization. In terms of motivation, we can say the following. CTR and CVR models and building them is a challenging task. Normally, these models operate on streams of data, and because we use the hashing tricks, item collisions can lead to performance decay. Interactions between different items, and especially different orders of these interactions, contribute differently to the final prediction. Existing DCN V2 addresses many, but not all of these challenges. We systematically investigated possible improvements, and we present these improvements in this work. So first of all, the architecture. We start from a stacked DCN V2 architecture, as you can see it on the leftmost side. However, with green, we marked the point of improvement. We touched all the cross layer, as well as similarity kernel, as well as the embedding layer. The latter is the focus of the first part of this presentation. So the collision-weighted mechanism is what we introduce here. For each embedding, we introduce a weight. These weights are learnable, which means that during models learning, they change. They're all initialized to 1, which means that in time, models tend to downplay impact of different embeddings. Because collisions have direct impact to embedding layer, we hypothesized that this already modulates impact of collisions. We also evaluated this impact via ablation studies. But before that, let's proceed with the collision weights layer definition. We define it as part of the embedding layer. We introduce an extra dimension of ones, so learnable parameters. During lookups, we first do a lookup, subset the first part to get the embedding, and the remaining column corresponds to weights. We do element-wise multiplications to get to the final embeddings, which are fed into the cross layer. In terms of ablation, we can say the following. We considered many ablation studies where for different proportions of data seen, because this is incremental online learning, we observe distribution of collision weights. We observe that if we decrease the hash space's size, there are more weights that are not 1, which means that less weights are actually close to the rightmost part of this plot, and more are closer to the leftmost part, which means that more embeddings get modulated in negative manner. They get downplayed. This effect is directly correlated with collision count, so at least to some extent, the two are related. Second improvement is the only dense layer. Here we started off from the DCN V2, we introduced initially, and we did the following modifications. We omit the direct multiplications with the input layer, so there are no element-wise preserving operations with the input when we iterate across cross layers. Second, we got rid of projection layer, which means that all this computation happens for all pairs, which is a bit computationally expensive towards a single, if compared against a single cross layer. However, as soon as we have multiple cross layers, which is normally what we require, we observe that we might need comparatively less only dense layers to achieve similar performance. And finally, because these are of same dimension, they get fused during compilation. So this only dense layer addresses the aspect of information loss cross layer. The final improvement is the similarity kernel layer, which is another layer we introduced on top of the embeddings. This is effectively a matrix multiplication with a transposed version of the embedding matrix, where we address the pairwise interactions. This addresses the explicit bias of modeling pairwise interactions, which seemed important in production, and also seemed something the initial deep and cross did not address directly. When we did offline benchmarks, we observed we get quite competitive performance, and also when we inspected different hash space sizes and just switching the type of embedding layer, so from the one used in DCN V2 to the one used in DCN squared, we observed superior performance. When we took the model online, we observed considerable KPI improvements for CTR as well as CVR. When scaling DCN squared, we observed quite a few issues. However, we got it done at the end. We first had to modernize the inference stack. We iterated a bit between TensorFlow and Onyx as the final inference engine. However, currently we stick to TensorFlow. We also optimized execution by implementing a custom fan-out batching strategy, which significantly reduced the latency. And final performance was obtained via iterative memory optimization, which enabled us to deliver more than 500 million predictions per second. So to conclude, we introduced DCN squared, an improvement over DCN v2 that addresses item collision issue, information loss in cross layers, and pairwise interactions being explicitly considered. As further work, we can use multiple embedding tables, policies for explicit modulation of collision weights, and investigation of hard resets at the collision weight level. Thank you for your attention.